So in this video we're going to be looking at esters, esterification as a reaction to produce esters, as well as ester hydrolysis, where we break them down into the constituents themselves. Now esters themselves, they actually look very similar to our carboxylic acids, but rather than having a hydrogen attached to the oxygen over here, we've got a variable alkyl group which normally comes from an alcohol, and then we've also got the carboxylic acid part of the ester, which also can have a variable alkyl group as well. Now when it comes to naming esters, we would look at first of all the part that came from the alcohol, which is the side without the double bond, and we would call that the alkyl group. So in the case of, let's say, one carbon atom, it would be methyl, 2 would be ethyl, 3 would be propyl, and so on. But I'll just call this alkyl itself. If I were to look on the left hand side, the side with the carbon oxygen double bond on it, we would look at the number of carbon atoms, and in this case, we've got a variable alkyl group. It could be anything really, so it could be ethanoic acid, propanoic acid, butanoic acid, but remember the ions that they form, you can end up with ethanoate, propanoate, and so on, and so we will call this a carboxylate part of the actual naming convention itself. Looking at some examples, you can see over here that we've got 2 carbon atoms over here, so I've got ethyl to start off with, and then on the left hand side, the side with the carbon oxygen double bond, I've got 3 carbon atoms, and so I'm going to end it in propanoate because I know that's come from the actual carboxylic acid, propanoic acid itself. Looking at the next one, I've got 3 carbon atoms over here on the side without my carbon oxygen double bond, and I'm going to have here again propyl in this case, and then on the side with my carbon oxygen double bond, I'm going to have 2 carbon atoms, so it's going to be called ethanoate because it's come from ethanoic acid itself. Looking at the next one, technically we had phenol over here, which is the similarity it has with alcohols in terms of the reaction. Although it's not an alcohol technically, we can actually involve it in an esterification reaction. So in this case, I would call it phenyl, that's my technical alkyl group. So it's going to be called phenyl. And then I've got 2 carbon atoms over here, so it's going to be ethanoate itself. So I've got phenyl, ethanoate all together. Now, if you were to think about your esters, we know there's 2 uses for them. One of them is as food flavorings, which, pear drops, they taste like pears pretty much, an artificial tasting pear, and they actually use esters in the flavoring of pear drops itself. We can also use them in perfumes, where a lot of perfumes, they actually have added esters because they dissolve pretty well in perfumes in terms of the alcohol and the base, and they actually have very nice smells itself as well. Looking at the following task over here, I want you to pause the video and have a go at naming the following esters itself. So in this first example over here, you've got 2 carbon atoms on your alkyl side, so that's going to be ethyl, and then on the side with your carbon oxygen double bond, you've got 2 carbon atoms, and that's going to be ethyl and then ethanoate itself. Looking at the next one, you've got again 4 carbon atoms over on this side, so that's going to be butyl, and then you've got 1 carbon atom over here, and then that's going to be methanoic acid, so it's going to be methanoate, butyl methanoate. Next one, you've got 1 carbon atom over here, so in that case you're going to say you've got methyl, and then you've got 4 carbon atoms all together over here from butanoic acid to form butanoate. The next one, bit trickier, you've got 2 carbon atoms over here, so you're going to say you've got ethyl, and then again you've got here benzoic acid on this side, so you've got a phenyl group over here, but you're going to call it benzoic acid, so it's going to be benzoate. Moving on then, if we were to look at the following, I want you to draw the structures this time of the following esters, and it might be helpful to actually start on the side which actually has a carbon oxygen double bond. Feel free to pause the video and have a go at the following. So yeah, going over this first one then, we've got butanoate, so we've got 4 carbon atoms, and then we're going to have an OH over here, and then we've got the carboxylic acid formed over there, and then we're just going to get rid of this hydrogen over here, and instead we're going to replace it with the ethyl part, which is 2 carbon atoms itself. Looking at the next one, you've got propyl ethanoate, so again ethanoate is going to have 2 carbon atoms, it's going to have a carbon oxygen double bond to the oxygen, but then that's going to be bonded to 1, 2, 3 carbon atoms like that. So I've got 3 edges and corners. Look at the next one, you've got 2 butyl propanoate. So in this case, propanoate, that's nice and easy, that bit. I've got 1, 2, 3 carbon atoms, carbon oxygen double bond, bond to the oxygen. But in this case, when you see 2-butyl, technically you've got butane, and you've got butane bonded at the 2 position in this case to the oxygen. So you're going to have a bond over here, that's 1 carbon atom, then you're going to have 2, and then you're going to have 3, but then remember you've also got carbon here, and you can clearly see that you've got butane, but the 2 position you've bonded to the oxygen itself. Look at the next one, you've got ethanoate, which is going to be 2 carbon atoms again, and then you're going to have oxygen. Think benzyl, think about an alkyl group where you've got benzene on there, and you've got technically phenol. Phenol, it can actually react in esterification reactions where you can form an ester, and so I'm going to have a bond directly into the benzene ring, and so that's going to form something that looks like this itself. And I've got here benzyl ethanoate itself. So moving on then, right, how do we actually make esters? Well, we call this reaction esterification itself. And in esterification, if we were to look at the first method, because there's 3 actual methods, the first method actually involves us taking a carboxylic acid and alcohol, heating them under reflux in the presence of a concentrated sulfuric acid catalyst. We actually make an ester, and then we actually remove a molecule of water itself, and so we end up with water as one of our products as well. This is known as a condensation reaction because water is actually being removed itself. Think about hydrolysis, water is being used up. Think about condensation, water is being removed itself. So you've got ethanoic acid, propan-1-ol, and what actually happens is you form propyl ethanoate. Remember, ethanoic acid is going to be what creates the naming convention of ethanoate, and then propan-1-ol, the alcohol, actually ends up forming propyl itself as well, which you can see the alcohol part is over here, and then the carboxylic acid part is going to be over here as well. But don't forget, the examiner could flip them as well. Now there's 2 more ways of making esters which give a much better yield compared to using a carboxylic acid and an alcohol. One of them we'll look at in this video, which is using acid anhydrides, and another method is in another video that's going to be using acyl chlorides itself as well. So moving on then, I want you to have got the following task, and I want you to draw the structures using skeletal formula and then name the first 2 esters formed itself as well. So yeah, in this case, we've got propanoic acid, which is going to have 1, 2, 3 carbon atoms. We're going to have that bonded to an OH, and then that same carbon atom bonded to an oxygen, double bond. We've also got here butan-1-ol. So in this case, we've got 1, 2, 3, 4 carbon atoms, but then on the 4th carbon atom, or the first one, you could consider it to be an OH itself as well. Now, under the conditions in that we've got H2SO4, and then we've also got here as well reflux, we know that we can end up forming an ester where we draw our carboxylic acid as normal, carbon-oxygen double bond, and then we've got an oxygen without the hydrogen, and then we're just going to attach the 4 carbon atoms on here, and it's worth you actually numbering them as well. So you end up with 1, 2, 3, and then 4 carbon atoms all together, and so that itself is going to be butyl because of the 4 carbon atoms on the side without the double bond, and then it's going to be propanoate itself. And don't forget, you also end up with a molecule of water. It is a condensation reaction. Looking at the next one, you've got benzoic acid, which is a benzene ring, carboxylic acid attached. Think about it as methanoic acid attached, and you end up with that reacting with, in this case, ethanol. So you've got 1, 2 carbon atoms and then an OH attached, and then you're going to have the same conditions as before. It's going to be H2SO4, and then you're going to have reflux as well. Now remember, again, you're going to end up with benzoate as an ion. So in this case, you end up with over here benzoic acid without the actual hydrogen on the oxygen itself, and then you're going to have 2 carbon atoms attached over here. Make sure you count your carbon atoms. You've got 1, 2 over here, so you've got 1, 2 over there. What would we name that? In this case, we call it ethyl, and then it's going to be benzoate itself as well. We also form water, and there's that one done. So looking at the next one, you've got 2-methyl propan-2-ol, 3-methyl butanoic acid, and you're going to end up with 1, 2, 3, 4 carbon atoms, and then you're going to have your carboxylic acid, which is going to be position 1, and then at position 3, you're going to have a methyl group that's going to react with, then in that case, 2-methyl propan-2-ol. So I've got propan-2-ol over here, and then I've got a methyl group at the 2 position as well. If I were to look at the conditions again, it's going to be H2SO4. I'm going to end up with reflux as well. And then I also end up forming the ester. So in that case, I'm going to draw my carboxylic acid out without the actual hydrogen on the OH. And then I'm going to have 1 carbon atom bonded to this carbon atom over here. And then I'm going to have 3 carbon atoms bonded to that as well. And there is my ester. And don't forget the water in there as well. So moving on then, previously we mentioned that you can actually make esters in a different way, and that is using acid anhydrides itself. Now acid anhydrides, they're made from the condensation reaction between two carboxylic acids. Could be the same carboxylic acid or could be different ones. In this example I've got ethanoic anhydride, and you can see the structural formula itself as well, where we've got the oxygen that combines the two acids together over here, and we also have the original carboxylic acids without the oxygen on there itself. Now looking at this, you can see I've got ethanoic acid over here, the OH comes off of that, and then the hydrogen comes off of this ethanoic acid over here, and that's what makes the molecule of water itself. So it is a condensation reaction. And then if we were to look at the anhydride actually formed, in this case you would call it ethanoic anhydride, because you've got 2 carbon atoms here and 2 carbon atoms here itself as well. Now if you were to look at another example where it's unsymmetrical, where if you were to split it down the middle, right, you can see that you've got 2 different kind of carbon chains on there. Let's say if you took ethanoic acid, reacted it with propanoic acid, you would form ethanoic propanoic in alphabetical order, and hydride itself, where you can see one side has 2 carbon atoms, another has 3 carbon atoms itself. Now if we were to actually form esters with acid anhydrides and alcohols, what we would do is we would warm the acid anhydride with the alcohol, and we would make an ester and a carboxylic acid itself. Now in this example over here, you're taking ethanoic anhydride. Again, you're taking one component of the actual acid anhydride, you react it with the alcohol, and you end up forming your ester over here, propyl ethanoate, but then your byproduct is going to be ethanoic acid itself, right? So it's going to be a carboxylic acid. Now if you've got an unsymmetrical, let's say acid anhydride, you could end up forming a variation of products as well. Now moving on, I've got an example for you to try. I want you to pause the video and have a go at the following. Remember to show your structures clearly and use skeletal formula itself. So looking at the first one over here, we're preparing methyl ethanoate from ethanoic anhydride itself. So looking at my reactant, that's going to be ethanoic anhydride. It looks like this, where I've got my carbon-oxygen double bond, and to that carbon I've got bonded oxygen, and then I'm going to have the same thing on the other side over here because it is going to be symmetrical. That's going to be reacting with something that we need to figure out, and I recommend that you always draw the structure of the product that you're trying to make. So in this case, I'm going to end up with methyl ethanoate. Think ethanoate, think ethanoic acid. You've got here ethanoic acid without the actual hydrogen, and that's bonded to 1 carbon atom like this. Now look at it, you can see you've got methyl, so in that case our alcohol must be methanol as we looked at before, and our byproduct isn't water, it's actually going to be just ethanoic acid, because that's going to be what's left over. Nice and easy because we've got a symmetrical acid anhydride. So in the next one, it's quite tricky. You can actually form 2 different products. The first one, the first equation, I'm going to go with ethanoic methanoic anhydride, and that's going to look like this, where I've got oxygen bonded to a carbon, double bonded to an oxygen. That's the methanoic part, and then the ethanoic part is going to be me having 2 carbon atoms and then a carbon oxygen double bond itself. It's going to react with, in this case, 2 methyl, and then it's going to be propan 1O, and that's going to look like this, 3 carbon atoms and then a methyl group over here, and then I'm going to have the alcohol over here as well. Now this first part of the equation is going to stay the same, but the thing is, it depends really which part that we actually use to make the ester itself. If we use this methanoic part, right, we end up forming 1 ester. If we use the ethanoic part, we end up forming another type of ester. Let's go with the methanoic part to begin with. So again, I've got methanoic acid over here, so it's going to be looking like this, bonded to an oxygen. Get rid of the hydrogen, of course, and then remember you form your bond over here to this carbon atom. You've got 1, 2, 3, and at the 2 position you've got a branch. So I've got 1, 2, 3, and then at the 2 position I've got a branch as well. And there I've got my ester, which in this case, right, you can see has 1 carbon atom that is on the side of the carbon oxygen double bond itself. Now my byproduct in this case, if I were to look at the other side, what's left over, well, we're going to end up with ethanoic acid, which looks like this. Now what about an alternative? Well, the first part is going to be the same, where we've got the same acid anhydride. We can end up with a different product. We can end up with 2 different products. This is the second one now. Again, we follow the same steps as before, but the only thing is when we look at the carboxylate part of our ester, we actually have ethanoate in this case, right? And then that's going to be bonded to oxygen, and then we end up with the same thing over here again. So 3 carbon atoms and a branch at the 2 position, but then our byproduct is just going to be methanoic acid, which is going to look like this itself. So moving on then, right, I've got another task for you to do. Feel free to pause the video and have a go at the following. So yeah, in this case, right, we need to think, okay, how do we form an ester? Well, we need a carboxylic acid and an alcohol. We must have an intermediate product over here as well. And we've got to think, okay, how can I form a carboxylic acid from this alcohol? Well, in this case, I'm going to need some reagents, which is going to be acidified potassium dichromate. So it's going to be K2Cr2O7. We're going to have H2SO4 as our catalyst. And then we're also going to have in there as well our condition, which is reflux. Otherwise, we could get an aldehyde, and so I end up forming ethanoic acid, which is my first reagent. Now, looking at my actual product that I need to make itself, the target molecule, I've got 2 carbon atoms, which is going to be the ethanoic acid part, and I must be reacting it with an alcohol, right? So we know we need to have H2SO4 as our catalyst over here, but in terms of our alcohol, what alcohol would it be? Well, look at where the carbon-oxygen bond is. You got 1, 2, 3 carbon atoms, so we know it could be propan 1-ol or propan 2-ol. Is it going to be propan 1-ol or 2-ol? Well, in this case, because our bond to the actual carboxylic acid, the O on there, is going to be over here, right in the 2 position, we know that we must actually have in there the alcohol, which is going to be propan 2-ol itself as well. Moving on, feel free to pause the video and have a go at the following. So yeah, over here I've actually got a cyclic ester, right, because I've got the carbon-oxygen double bond, but then if we go around the chain, right, it actually meets up with the other side. If we've got H2SO4 and reflux as our condition, there's only one reactant we can have, and we can take a look at something that actually has a carboxylic acid and an alcohol group on it. In this case, because you're dealing with a cyclic structure, you would have to number the carbon atoms. You've got 1, 2, 3, 4, and then 5 carbon atoms over here. So in that case, I'm going to have pentanoic acid, right? So in that case, I end up with pentanoic acid. So I've got 1, 2, 3, 4, 5 carbon atoms over here. My carbon-oxygen double bond and an OH. And remember, you need to have an alcohol at the other side. So in this case, I'm going to end up with an alcohol coming at the 5th position itself as well. So I'm going to draw my structure out like that, right? Check if it's right. 1, 2, 3, 4, 5. Numbering always helps. And in this case, I've actually got 5-hydroxy. And then it's going to be pentanoic acid. And if we react that with itself, you can end up forming the following structure. Now, you could actually end up forming another product looking at this. You can actually take 2 of these carboxylic acid / alcohol molecules, and you can combine them together in a straight chain as well. So you can end up with a reaction where you actually end up forming an alternative product where you end up with 1, 2, 3, 4, 5 carbon atoms again, carbon-oxygen double bond. You've got an alcohol attached over here to the 5th carbon atom. You've got oxygen attached over here, but then that's going to be attached to, again, 1, 2, 3, and then it's going to be 4, 5 carbon atoms, and then you end up with a carboxylic acid over here as well. You can get either one of these 2 products. Either one's fine. So moving on, feel free to have a go at the following. A bit more trickier, and you've got to think about different parts of chemistry in terms of what product you can form. So yeah, in this case, we've got to look very carefully at our actual molecule itself. And we can see that we've got here, first of all, in terms of our functional groups, we've got an ester. And we know that ester must have been formed from a carboxylic acid and an alcohol. Look at the carboxylic acid part. It's going to have to be benzoic acid in this case, because that is what's attached towards the side with the carbon-oxygen double bond, right? This is going to be called benzoate. That's what it ends with. I have no idea what it starts with because that looks a bit too hectic to me. But what am I going to actually have to add to that? Well, I know in terms of my alcohol itself, right, that's going to be this region over here. So I'm going to end up with cyclohexane. That looks like this. And then over here, I'm going to have an alcohol attached, and that's going to be cyclohexanol. If I were to look at the actual acid, we know it's benzoic acid. How do we actually form benzoic acid? Well, we've got to think, okay, right, we must actually have a alcohol attached over here somewhere, but we can't actually form an alcohol from a ring of benzene itself directly from our specification of OCR. So what can we actually have? Well, we can actually have an aldehyde itself that we can oxidize under the conditions of reflux to actually get a carboxylic acid. So I can actually have benzaldehyde, which looks like this itself. Now we know we can actually do acylation over here. We can do Friedel Friedel-Craft's acylation, where we end up forming a bond, because you've got to think where your bond's being formed between this carbon that's double bonded to this oxygen over here and this benzene ring itself. Remember, electrophilic aromatic substitution. You've got an acyl chloride, which in this case is going to be methanol, and then it's going to be chloride itself, right? So you end up with something that looks like that. You need a halogen carrier catalyst, where I'm going to use Al, and then it's going to be CO3 itself as well. And that together will make benzaldehyde. Well, how do you oxidize benzaldehyde? Well, you will use acidified potassium dichromate. So you've got potassium dichromate here, and then you've got H2SO4, and then don't forget the reflux as well, because you're forming a carboxylic acid itself. And there is our big massive synthesis map. The only thing that's missing is the H2SO4 over here, because we need an acid catalyst to actually catalyze the reaction between our carboxylic acid and our alcohol itself. So moving on, in that case, we've looked at how we can make esters. What about if I wanted to do ester hydrolysis to actually break apart an ester into its constituent carboxylic acid and its alcohol itself? Well, hydrolysis is actually the opposite of condensation. In this reaction, we use water to break down a compound itself. Now, there's two types of ester hydrolysis that you need to be aware of. The first one is acid hydrolysis, and in this case, you would use HCl and reflux. You put that above the arrow, but then in terms of your reactant in the balanced equation, you show water. And then there's base hydrolysis, otherwise known as alkali hydrolysis, where you show sodium hydroxide or whatever base you're using as the actual reactant itself, but then you put water and reflux above the actual reaction arrow. Now, in both cases, you're going to end up with ethanoic acid and ethanoic acid, but then in this case, right, you actually form sodium ethanoate itself, because you've got base in there. That excess base is going to actually react with the actual carboxylic acid that forms. So technically, you actually form salt itself, which is going to be sodium ethanoate in this case, because we've used sodium hydroxide as our base. Now, in both cases, you still form an alcohol, which is just the same as the reactant that you use to make the ester, but just be aware about the what goes above the arrow, and then what you react with your actual ester, and then what product you actually form as well. So moving on, right, I've got a task for you to do. Feel free to pause the video and have a go at writing the balanced equations for the following. So in this first case over here, right, I'm going to start off by breaking up my actual ester, and I've got acid hydrolysis, so I don't need to worry about any of the products. My carboxylic acid part is going to be the side with the carbon-oxygen double bond, and so I draw that out as I see it. So I've got 4 carbon atoms that's bonded to an oxygen and a hydrogen, and then I've got my double bond to oxygen there, and a methyl group over there. So I've got 1, 2, 3 methyl butanoic acid itself, and then I'm also going to end up forming my alcohol, which in this case you can see the bond is to the second position, so that's going to be propantool itself as well. Now, what do we actually put in terms of the reactants? Well, I'm just going to have 1 lot of water here, because I've got 1 lot of ester hydrolysis taking place. Looking at the next one, right, it's quite clear in this case. Again, we're going to react it with water, because we've got 1 lot of ester hydrolysis taking place. Again, we've got ester bond that we need to break. We've got here benzoic acid, which is quite obvious and straightforward, and then we've got our carbon oxygen double bond, and then a bond to the OH. And then I'm also going to end up with my alcohol, where I've got 1, 2, 3 carbon atoms, and so in that case I end up with 3 carbon atoms, and then OH bonded to that 3rd carbon atom itself. So I've got propan, and then it's going to be 1O, right, a different product compared to what we had in the last reaction. So we've got acid hydrolysis over here. Have got the following task, but this time with base hydrolysis. Just be careful with what products you form and what they react with as well, especially for B. So again, over here, I'm going to react it with sodium hydroxide, and then what I'm going to end up forming is, in this case, the nice easy part, I've got propanoate, so it's going to be propanoic acid. That's nice and straightforward, but just remember, you don't actually form propanoic acid. It's going to react with the sodium hydroxide, and what you actually end up with is an ionic bond between the sodium ions and the oxygen that's negatively charged, so you end up with sodium propanoate. Your alcohol remains unchanged, and so what you actually end up with is, in this case, because you've got 2 carbon atoms, it's just going to be ethanol. The next one's a bit tricky in terms of balancing the equation, looking at the product. Again, you've got carboxylic acid over here, you've got an ester in the actual molecule over here as well, and then think about what products you actually make in this case and what they actually react to for. So in this case, we're going to react it with sodium hydroxide, 1 lot to begin with, and so for my products, I'm going to end up with my benzene ring. Again, we must have phenol, It's not an alcohol, it's phenol, it's its own thing. We've got carboxylic acid over here, and then we've also got our other carboxylic acid, which is going to be the one that was involved in making the ester, which has got 2 carbon atoms, so it's going to be ethanoic acid. Now, if you got that answer as being your correct answer, that's unfortunately wrong, because remember, we've actually got here base hydrolysis, so that sodium hydroxide, one lot will react to break the ester bond, another lot will react with this carboxylic acid group over here, and another lot will react with this phenol group over here. So in that case, I need to get rid of this hydrogen over here, get rid of this one over here, and then I get rid of this one over here, and what I end up forming is a minus charge here, and then a positive charge for the sodium, a minus charge here for this phenoxide part, and then a positive charge for the sodium, and then again the same thing for this carboxylic acid, which forms a carboxylate ion, an ethanoic ion, which is also going to be sodium, and then positive charge over there as well. And so I need 3 lots of sodium hydroxide to get this to react. A very challenging and a very tricky question, that one.